We're going to explore a little more how and when you could use this potential function phi. So here's an example given by Frank White in his very good book on fluid mechanics. So imagine two blunt objects that are being approached by a free stream of velocity, u something or other, here. So this is a free stream flow. So when can we use potential flow theory? Well, we definitely can use it out here in the free stream. This is clearly irrotational flow out here. And we can treat this as inviscid if the Reynolds number is greater than 10 to the fourth. So that's the rule of thumb he gives, that if it's greater than 10 to the fourth, based on, I guess, the gap height here, though it's not said explicitly, then you can treat this as, as inviscid in many of the regions, but not all of them. So there's an inviscid core. We know this. There's going to be an entrance region here before viscous effects take over. So if that L over D is less than 10 in that region, that would be here, right? This is your entrance length. That's a region where we can treat this as inviscid. So you can use potential flow theory to cover the undeveloped region of the flow between these two objects. Now, past this point, the two boundary layers, the viscous boundary layers have merged. We know this. The entrance region ends. Now you have a totally viscously dominated flow in here. So that's now flow between two plates or flow in a pipe where you've got viscous effects dominating everything. So that's going to be what happens there. But out here, the boundary layers haven't grown yet. The viscous effects are confined to the narrow region in the boundary layer. And in the core here, we can treat this as inviscid flow and use potential flow theory. We have stagnation pressure at the two objects, the blunt objects at the front of the objects here. So that's going to be a known pressure. And then we can use potential flow theory along the outsides of these objects up to some point. So outside the objects, again, viscous effects are confined to a very, very thin boundary layer for this high Reynolds number. If you have a lower Reynolds number, of course, the viscous effects would be much larger and you wouldn't be able to do this. But at a high Reynolds number, the boundary layer is very thin. And so you can treat this as the most of the flow out here is inviscid, and you can calculate pressures along here using the Bernoulli equation. You know the pressure at the stagnation point, and so you can calculate pressures based on changes in velocity, because the velocity at the stagnation point is 0. You can calculate velocities out here near the surface, treating it as inviscid, and then calculate pressures on the surface, and thereby try to calculate lift. And so people use this to try to calculate lift on objects before we had the ability to model them directly using computers. Back here, the flow starts to separate. You get this turbulent wake. You're not going to be able to do anything out here with inviscid flow theory. Obviously, once you have turbulence, you're going to have viscous effects all over the place with spinning and swirling and lots of rotation. So it's going to be highly, lots of vorticity out in the wake region and lots of viscous effects. And so you can't use potential flow theory anymore. So it's only going to be useful in certain regions. But it can be useful in these regions. So inviscid core out in the free stream, and then as you come along the surface until the wake really starts to build, or the turbulent boundary layer really develops and becomes large. All right, so that's that. What would your boundary conditions be for phi? So we can look at, if you were going to solve this partial differential equation, the Laplace equation, you need boundary conditions. That's always true whenever you're solving a PDE. As engineers, you must always be looking for those boundary conditions. So the boundary conditions that you'd hope you'd know d phi dx, d phi dy, and d phi dz at the boundaries. So that would be knowing u, v, and w on the boundaries. And the other one is you would know if there's a surface that there would be d phi dn would be equal to 0 there, because that means there would be no penetration at the surface. There'd be that's a no penetration condition. That is, fluid does not move through, into, or out of solid objects. So that's what that is telling you. However, there is slip on the surface. So the surfaces do have slip. That is, they have velocity tangential to the surface. They are not no-slip surfaces. They're not no-slip surfaces because there's no viscosity. And what causes the no-slip condition is the viscous effects. But because there is no viscosity in potential flow theory, there is a slip condition. So the velocity can be high along the surface, but it cannot go in or out of the surface. So those are your boundary conditions: no penetration on surfaces, and then hopefully known velocities on the actual boundaries. And that allows you to solve the equation del squared phi for a given domain.